Scientists have discovered ingredients regarded as crucial to the origins of life in a comet. The amino acid glycine has been found in the cloud of gas and dust surrounding the Rosetta Comet, which European Space Agency's Rosetta spacecraft has been studying for the past 2 years.
Glycine is regarded as one of the building blocks for life. Avionics engineer Warwick Holmes helped build the Rosetta spacecraft, and he joins us now. How satisfying is it for you, Warwick Holmes?
Well, this is what the whole mission has been about.
Yeah.
This is to try to prove that this fundamentally important chemistry has been found on the comet 4.7 billion years ago, and they believe that this is then transported to Earth to help start life on Earth.
Is it fair to say, Warwick, that we ourselves are made up of these crucial amino acids, which may have been brought here by comets?
Andrew, indeed. I mean, this is what they really believe is the primary mechanism for the formation of life on Earth. Earth was first formed, it was a red-hot ball of molten magma. 1.3 billion years later, a secondary bombardment of comets came, and that brought what they believe was water, and now we've confirmed the amino acids, which we think kick-started the development of life. So water by itself wouldn't have done that. We needed the additional carbon chemistry. This is a model of the comet. And the reason it's black is because it's frosted with this important organic carbon chemistry. And this is what we've announced in the last 24 hours. They've actually confirmed glycine has been found. That's one of 20 of the amino acids found in the human body. And that was now confirmed to have been formed 4.7 billion years ago on comets.
It's fascinating as well when I was reading more about the detail of the structure of the comet and how these particular amino acids have been discovered, because the surface of the comet itself is quite cool, yes, but it's above this particular atmosphere around the comet where we're seeing these sorts of things develop.
Indeed. No, we've been very lucky that we've been following the comet for almost 2 years now, and we've actually gone through the perihelion passage, they call it, which is where the comet goes past the sun. This activates the comet, it evaporates this important chemistry which is inside the comet, and the Rosetta spacecraft is only 7 kilometres at the moment over the comet, and we've been swooping down and picking up some of this gas and dust and material, and that's from the surface, and it turns out that this is where we found the amino acids.
As you said, Warwick, I mean, this is exactly what you deployed the spacecraft for, to try and detect this sort of thing. How satisfying is that for you? And just explain how difficult the logistics and the engineering of this mission itself.
Well, Andrew, the mission really started 25 years ago. I mean, the initial planning, the design, the building took 5 years, it took 10 years to get there, and it's been heralded as one of the most complex interplanetary spacecraft missions that's ever been attempted. To actually even get to the comet was history in the making. To put the little philae lander onto the surface as well, which were operated for 3 days, and to continue orbiting now for almost 2 years, and to find these amino acids. This has confirmed one of the most important theories that we've had in the formation of life on Earth. And to actually go in situ directly to a comet and make that kind of measurement, that complexity, this is with a mass spectrometer we have on the spacecraft. We've got an atomic force microscope. These incredibly complex instruments have been taken to the comet to do this kind of experimentation.
I mean, I do note that we're talking about something that's some 6.4 billion kilometres from Earth and travelling at a speed of around 66,000 kilometres an hour.
Absolutely correct. It took 6.4 billion kilometres just to get there. That was the start of the mission. And so we've now been following it for about an extra 1 billion kilometres. And yes, these are huge numbers. It took 10 years of flying to get there. So that was even before we could start making these measurements. So to have a spacecraft that could survive for that long was an incredibly complex, very difficult mission. So,
Warwick, as you say, there were sort of two parts to this mission. You had Philae, which landed on the comet. So what stage, is Philae now dead? You're not getting any more information from that?
No, poor old Philae is dead. It lasted for 3 days. We wanted it to wake up 3 months later using its solar cells. Unfortunately, it bounced when it did its landing, but it did come down again. It did do science for 3 days. We wanted it to wake up 3 months later. It did actually wake up 7 months later, but the problem then was we were so close to the sun, Rosetta had to move away and we couldn't actually hear it talking to us. But it did its first 3 days of primary science, confirming, again, this chemistry on the surface and many other measurements. And so, that yes, you're right, there were two parts to the mission. The little lander, which weighs about 100 kilos, and the big mother spacecraft, Rosetta, which is still in orbit, and will be until September this year, when we put Rosetta also down onto the surface of the comet.
Now, if we believe, as this discovery seems to confirm that comets are part of a process where we're seeding life forms in the universe. Can we infer from this that it shouldn't be that remote possibility to find other kinds of life forms out there?
Miriam, this is absolutely correct. What this really confirms is that this is a generic mechanism, in that all the stars, we've confirmed now many times that there are other planets around other stars. This process of planets being left over when stars are formed is generic. And together with that now, we've confirmed that this carbon chemistry being formed as the precursor of the formation of the planets. This is really an incredibly significant discovery, because it really implies that there could be life throughout the entire galaxy and universe, in fact. This is proof that there's this mechanism which creates life, whether we want it or not.
And Warwick, it also goes to show that we don't need manned missions into the solar system to discover this sort of thing.
No.
However, having said that, we've got some news today that NASA has successfully tested an inflatable room, if you like, that's been blown up next to the International Space Station. Here are some pictures. This is pretty impressive in itself, isn't it? Because what will this lead to, particularly if we are looking at manned missions again to the moon, perhaps, or even Mars?
Indeed. What this shows is we now have the technology where we can have like an inflating room. And so the volume can be folded up into a much smaller space, and we can launch that and inflate it using oxygen. What is really important here is that this material has to be extremely strong, because it's like the material of a bulletproof vest. But it also has to withstand incredible ultraviolet light. The ultraviolet light in space is much harsher than what we have here on Earth, and we can see what effect that has on plastics and the bleaching effect it has. So for this material to be safe and to have a pressurised volume which humans can live inside, it's got to be extremely reliable and extremely strong. This technology has now been verified by this mission, and that means we can open the situation now for having very large volumes created, which can unfold in space and has a habitable volume for humans to live in.
Now, as you noted, just with the unmanned mission, with the Rosetta spacecraft, incredibly difficult to get that particular machine on its own out into that part of space. Very challenging to see manned missions going beyond the point where we've seen them previously.
Well, it's a combination of the two, in fact. I mean, the success of the Rosetta mission was based on the fact that a lot of intelligence was built into the spacecraft. It had to look after itself. The distances it was going were so far that the speed of light delay meant that if something went wrong, we couldn't react fast enough. So we had to build the intelligence into the spacecraft, and the redundancy and the reliability. That, together with the human systems, means that we can have a combination now of incredibly complex interaction between intelligent machines helping humans and humans helping the machines. And so the next step is, I don't know, a manned landing on Mars. I still think that's a long way away, but it's proof that technology is evolving and is now getting there. So I won't make any predictions when I think that's going to happen, but it's a combination of the two, in fact.
Yeah, and just before you go, Warwick, I know when we spoke to you, along with Dr. Carl recently, you were disappointed the fact that Australia is not on board here with these space missions, and it could be for not such a huge outlay either.
I mean, there's been a lot of discussion about Australia's emerging innovation, or interest in innovation and technology. I'd just really like to see either of the governments involved to make that commitment, because there's a lot of incredibly exciting engineering going on, and I just feel that in many cases Australia's been missing out. So I really would like to see this commitment to innovation really manifest itself in something actually happening.
Well, the results speak for themselves. Warwick Holmes, very good to have you on the program.
Thank you very
so much.
Thank you.
Let's stick with technology, and Melbourne researchers have developed a robotic arm which could help amputees regain their sense of touch.
The technology could send and receive signals from the brain.
This technology could help revolutionise care for amputees.
Essentially, it will be a limb